In order to calculate the surface area for a three-dimensional function over a two-dimensional domain, we'll use this formula which involves double integrals. We do need for this surface function to have continuous first partial derivatives, and we'll integrate over that domain region. So let's look at an example. We're given a surface function, and we're asked to find the surface area of the portion of the surface that lies above the xy plane. So in order to determine the domain region, we probably need to graph this thing. So since I don't immediately recognize it, I'm going to throw some algebra at it to see if it becomes more recognizable. Let's get the x squared and y squared terms positive and by themselves on one side, which will leave us 4 minus z on the other, and it may be a little more recognizable if we factor that negative out of the z side to get this equation. So now we can see that if we sliced it with constant z-planes, we would get trace curves that are circles. Notice if my z-planes are too big, I don't get a trace curve. And so this might be enough for us to see that we have a vertex point of 0, 0, 4 that's opening down to give us a trace curve that is a circle of radius 2 in the xy plane. And so basically we're getting a circular paraboloid opening down from this vertex point, and we're being asked to find the surface area of the region that lies above the xy plane. So now I can see that the domain region in R2, over which we're going to integrate, is a circle of radius 2. So now let's set up our integral to calculate that surface area. So this is our domain region D in the xy plane, and we'll be integrating over D. We do need to find the first partial with respect to x and the first partial with respect to y in order to build our integrand. So let's go ahead and find that. First partial with respect to x is going to be the partial derivative of our z function with respect to x, which is just negative 2x. The first partial with respect to y is similarly going to be negative 2y, and therefore our integrand is going to be 1 plus. First partial with respect to x is negative 2x, quantity squared. First partial with respect to y is negative 2y, quantity squared. And for right now, we'll just say dA because we haven't yet decided our limits of integration. Now, since our domain region is a circle, my first instinct is to convert everything into polar coordinates, in which case I'd need to think of a little tiny polar rectangle and decide if I want to integrate with respect to r first or if I want to integrate with respect to theta first. Since we have a nice well-behaved circle, it actually doesn't matter. I'm going to choose to integrate with respect to r first, and my r limits would be going from 0 to positive 2. So now we'll convert everything into r's and thetas and integrate with respect to r first. This integrand is going to simplify to being 1 plus 4x squared plus 4y squared. And let's recall that our substitution for x squared plus y squared is r squared, which is going to make this integrand 1 plus 4r squared. Let's also recall that the area of a little tiny polar rectangle is either going to be r dr d theta or r d theta dr, depending on the order of integration that we choose. We are choosing r dr d theta. Again, we said that our r limits go from 0 to 2. And then once we have a band that is added up in the direction of the r, the lowest extreme for that band is going to be when theta is equal to 0. And we'll need to sweep it all the way around to get theta is equal to 2 pi in order to cover that entire domain region. So now we're ready to integrate, and the inside iteration is going to be the integral from 0 to 2, square root 1 plus 4r squared, r dr. And now we'll use u sub in order to calculate this integral, where we let u equal to 1 plus 4r squared, and du will be 8r dr. So we need a factor of 8 in here, and we fix that up by multiplying by 1/8 on the outside. So now we have 1/8 times the integral of u to the 1/2 du, which is 1/8 times 2/3 u to the 3/2. We need to go back to r, and this becomes 1/12. We'll pull all those constants to the outside. 1 plus 4r squared to the 3/2, which is evaluated from 0 to 2. So we plug the upper limit of 2 into the antiderivative, and from that we subtract the lower limit of 0 plugged into the antiderivative. And this simplifies down to being 1/12 times 17 to the 3/2 minus 1, a constant. This constant is going to become the integrand in the second iteration. And so we have the integral from 0 to 2 pi of this constant, d theta, and the antiderivative is basically going to be that constant times the angle theta, which is then going to be evaluated from 0 to 2 pi. Let's keep this constant multiple on the outside and plug the upper limit 2 pi and the lower limit of 0 into our antiderivative theta, which is going to give us our ultimate answer for the surface area, which can then be simplified just a tad to give us our final answer, pi over 6 times this constant. And since this is surface area, we would say that the units are going to be square units.